Welcome to this explainer. Today, we're diving into a DIY design document that is honestly pushing the absolute boundaries of off-grid agriculture. We are talking about a continuous flow, solar-powered, plasma-activated water system specifically designed for hydroponics. If you're into self-reliance and hardcore engineering, buckle up. Let's kick things off with a pretty wild question that drives this entire engineering journey. Can we create highly effective fertilizer using literally nothing but air, water, and electricity? I know, it sounds a bit like alchemy, but as this design document outlines, it's very much grounded, real-world science. The answer to that question, plasma-activated water, or PAW for short. Basically, when regular water gets zapped with atmospheric pressure plasma, it generates what we call reactive oxygen and nitrogen species, or RONs. Suddenly, your basic, everyday water is infused with vital nutrients like nitrates and hydrogen peroxide. Peer-reviewed studies actually show this activated water can massively boost seedling biomass, increase fruit numbers, and just generally supercharge overall plant growth.
Don't worry if this sounds a bit like sci-fi. We're going to break this entire machine down logically, piece by piece. Here is our agenda. First, the magic of plasma water, then the core system architecture, designing the treatment chamber, solar power and energy, integration with hydroponics, and finally, some crucial safety and next steps.
All right, let's jump right into Section 1, the magic of plasma water, scaling up the Skyforge. Moving right along to Section 2, core system architecture. Let's look at the big picture. Now, what's really cool to see here is how the paths of solar power, high voltage, and water all kind of weave together. The goal is taking that original tiny benchtop Skyforge concept and scaling it way up into a continuous 5 to 20 liter per hour hydroponic beast. You've got your solar power feeding in, the high voltage spark doing its thing, the water flowing from the inlet straight to a holding tank, and finally feeding right to your plants. It's literally a beautifully closed loop. To really wrap our heads around the complexity of this beast, we can organize it into 6 critical subsystems. We've got our off-grid solar generation and storage, the high-voltage plasma generation, the actual treatment chamber itself, fluid handling, automated sensing, and of course, the hydroponic interface that feeds your crops. Section 3. Designing the treatment chamber, or as I like to call it, catching lightning in a bottle. Take a look at this pin-to-water corona configuration. See that array of sharp tungsten pins hovering just like 5 to 15 millimeters above the water surface. By running high voltage through those pins and using the water below as a grounded cathode, you're basically creating miniature lightning. It dances right over the water to maximize the exact area where the plasma and the liquid meet. Now, if you want higher yields, you really have to optimize that geometry. The standard pin-to-water setup is definitely simpler to build. But check out the vortex chamber approach. By using a tangential inlet, it creates this swirling whirlpool effect. This drastically increases the total surface area where the plasma actually touches the water. It's a massive design trade-off that's definitely worth considering if you want maximum efficiency. Okay, Section 4, solar power and energy. This is all about powering the plasma. To run this thing entirely off the grid, we rely on a solar and lithium iron phosphate, or LiFePO4 architecture. That gives us the 50 to 200 watts we need to handle those intermittent high voltage loads. And why LiFePO4? Well, for a rugged outdoor setup like this, you just can't beat its safety, incredible cycle life, and sheer reliability compared to standard batteries. All that solar power feeds into a zero-voltage switching driver and a flyback transformer to generate a massive 30 to 60 kilovolts. That is a ton of voltage. But here is the clever part. It's current limited. This gives you that highly reactive, non-thermal corona effect without just melting your electrodes into a puddle with a massive high current arc. For all you off-grid engineers tuning in, here are the concrete sizing guidelines you need to precisely calculate your solar array and battery requirements. Let's put this into perspective. If you're running a typical 100-watt load for 4 hours a day, you need about 400 watt-hours of daily energy. To sustain that, pairing a 200 to 400-watt monocrystalline solar array with a 100 to 200 amp-hour battery is going to give you the comfortable margin you absolutely need for those cloudy, overcast days. Moving on to Section 5, integration with hydroponics, getting this from plasma to plants. Now here is a crucial detail. POW chemistry isn't stable forever. You can't just bottle this stuff and leave it sitting on a shelf in your garage for a month. The reactive species will actually degrade over time. That's exactly why you have to process and circulate the treated water right near its final point of use. And of course, you've got to strictly monitor your pH, your electrical conductivity, and your nitrates to make sure you're supplementing your plants perfectly. So the fluids journey goes exactly like this, step by step from the source water straight through that high voltage plasma treatment chamber, down into a holding tank, and then finally directly to the plant roots. Whether you're running a deep water culture, a nutrient film technique, or just a simple drip system, this specific integration pathway guarantees your plants are getting the absolute freshest, most nutrient-dense, activated water possible. Finally, Section 6, Safety and Next Steps. We really need to drop the fun science tone for a minute and focus on some crucial warnings. Let's get real for a second. High voltage and water are a potentially lethal combination. We're talking serious, life-threatening hazards here. Physical isolation, strict safety interlocks, and bulletproof weatherproofing aren't just polite recommendations. They are absolutely non-negotiable for outdoor survival. The system has to be designed so that the operator can never, ever accidentally contact a live electrode. I really want to emphasize this stark warning straight from the design document. It explicitly states lethal current is possible. So never work alone and always, always verify your compliance with local electrical codes. Also, keep in mind that the ozone generated in this process isn't just tough on plastic seals. It is a serious respiratory irritant. Proper ventilation and smart material selection are totally vital. So, to actually build this safely, you really need to follow this highly recommended development sequence. Start with basic bench skill tests before you even think about hooking this up to a controlled plant trial. Seriously, don't build the whole thing at once. Scale the chemistry first, measure your real power draw, then build out the solar setup to match. And when you finally are ready to test on plants, always do side-by-side trials with an untreated control group. You definitely don't want to accidentally shock your entire crop with crazy unbalanced pH or way too many nitrates. Which leaves us with one incredibly exciting thought to ponder as we look toward future refinements like closed-loop nutrient control. If we can generate highly effective fertilizer from literally nothing but thin air, water, and sunlight, how else is DIY plasma technology going to completely revolutionize off-grid farming? The frontier is wide open right now. Thank you so much for joining us for this explainer, and we will definitely catch you on the next deep dive.